In this lecture, we're going to look at the 4 frames that we use to denote the position and attitude of the aircraft. And we're going to develop a transform that will allow us to go between the body frame and the inertial frame, or vice versa. So let's jump in by looking at just a 3D depiction of our aircraft. So what we see here is the northeast down frame plotted, so NED, plotted with the aircraft in a particular configuration. And what we want to do is we want to define a reference frame. Oops, let me go over there. A reference frame, the body frame, where we have in the body frame, if we take a look at it, the x-axis is pointing out the nose of the aircraft. The y-axis is pointing out the right wing. And the z-axis is pointing out the belly of the aircraft. So we're going to do that by transforming between 4 different coordinate frames. Okay, the first coordinate frame we're going to look at, whoops, we want to keep that one. The first one we're going to look at is we want to just transform between the body frame and the NED frame and the vehicle frame. And the thing you'll want to notice here is that our axes are parallel. So all we've done is we've taken the origin of our reference frame in the NED frame, and we've defined a new origin in what we call the vehicle frame. So let's take a look at that. Okay. So we have our inertial and vehicle frame, and like we just saw, the axes are parallel, right? So our k-axis, z-axis, still points directly into the middle of the Earth. J points east, and I points north. It's just that we've now have this new center. I didn't really draw that line. It'd probably be easier to just use a line. We've gone from one origin to another. And look at that. Now I can put an arrow on it. Okay, so all we've done is move the origin. So this is pure translation, right? And if we were to write this, our origin in frame FV, so we call this our vehicle frame. So this is the origin is equal to in frame V is equal to 0, 0, 0. This is going to be equal to we're going to have the origin in frame, there we go, this is frame V. The origin in frame NED is going to be equal to what we call our north position, our east position, and our down position. And note that P sub D is the negative of altitude. Okay, so this is just a really simple translation of our vector frame, or of our coordinate frame. So the next one we're going to do is we're going to start aligning our axes to be aligned with the vehicle. And we're going to do that by considering 3 different Euler angles. First is our heading, or often referred to as our yaw angle, and we'll see that here in just a second. Then we'll jump into our elevation angle, or our pitch angle, and we also will end with our roll angle, or our bank angle. And by the time we've gone through these 3 rotations, instead of having the axes parallel to the northeast down frame, they'll be pointed out or aligned with the vehicle like we just saw. Now there is a drawback. We do have a mathematical singularity. We've talked about that in previous videos. And we can just convert these Euler representation over to a quaternion. So vehicle 1 reference frame, the only thing we've done is we're going to take our system, and we're going to rotate it with a z-axis rotation. Remember, z in our vehicle frame is pointed towards the center of the Earth. So in this case, we have, or pointed down. So in this case, we're going to take a rotation about the z-axis. So this is r, z, and we're going to rotate about psi. Now, the goal of this is that if we're to project down, looking from the top down, what we want is that this vector I in vehicle 1, this is going to be aligned. This will be aligned with the projection of the nose in the northeast frame. Not the frame, in the northeast plane. Excellent. So we're just going to do that by what's called our heading angle. So this is much more easily seen in the graphic to see what we're talking about. So jumping back over to the graphic, we had our vehicle frame. So now let's look at our vehicle and our vehicle 1 frame. So all we've done, so first off, the words write all over each other, so we'll fix that in just a second. But what I want you to see is that we've done a rotation about our z-axis. So the z-axis is the same in both the vehicle and the vehicle 1 frame. Okay, so now we can stop looking at our vehicle frame and we can look at our vehicle 1 frame. Now what you're going to want to see is that the nose is, if we projected it up into the northeast plane, that it's running parallel with this red vector. The easiest way to do that is if we're going to just do a top-down view. Whoops. So again, now if we have a top-down view, we've just projected everything into that northeast plane, and that vector now aligns with the direction of the nose in that northeast plane. And I want to make sure it's very clear that it actually does not align perfectly with the nose. So if we come in here and we take a look, our nose is the x-axis here in red is not pointing out the nose. It's the projection of the nose in that northeast frame. Okay, so that's our first rotation. Then we're going to jump into the second rotation. We're going to define this angle theta, and what we're going to do is we're going to rotate. This is rotating about the y-axis, and what we're going to do is we're going to take the nose of our aircraft. Well, we're going to take the I vector and align it with the nose of our aircraft. So we had I in vehicle 1, and I do apologize, in the 3D graphic we had it pointed down. But what we're going to do is we're going to define a new frame. We'll call it the vehicle 2 frame, where all we're doing is we're doing a rotation about the y-axis until the I in the vehicle 2 frame aligns with the nose of the aircraft. Again, so the rotation, the transform to get from the vehicle 1 frame to the vehicle 2 frame is just this rotation, or this y rotation by theta. Okay, so let's take a look at that. So again, we're displaying over here the vehicle 1 frame, and we can see that the x-axis isn't pointing directly out the nose. And so if we look at the vehicle 2 frame, the first thing to notice is that we've rotated about the y-axis, so they share y-axis. So all we've done is we've rotated about the y-axis. And now, if we get rid of the vehicle 1 so that we can see vehicle 2 better, we'll see that the x-axis is coming out of the nose of the aircraft. Now, the other two axes aren't aligned with the aircraft, and they're really not necessarily aligned with anything meaningful. But we've now defined a frame where the x-axis is coming out the nose of the aircraft. Okay, so the next step is now we want to align the frame, or define a frame that'll be aligned with the body of the aircraft. So our third rotation is just going to be a rotation from vehicle 2 frame to the body frame. And this is just an X rotation. And we're going to define the rotation that we need. We define that as phi, where now we're going to rotate about the x-axis, where we will then define the J until the J in our body frame aligns with the right wing. And the I axis already aligns with the nose of the aircraft. And then the result will be, if we do I cross J, that the K vector, this will point out the belly of the aircraft. All right, so if we come back here and take a look at that, so we'll zoom out just a little bit, and then we'll visualize the body frame. And the first thing again to notice is that they both share the same, the vehicle 2 and the body frame share the same axis, or share the same x-axis. So that red axis is the same for both of them. And then if we get rid of vehicle 2 frame so we can just see the body frame, again, it's what we showed at the beginning, that the x-axis is pointed out the nose of the aircraft, and then the y-axis is pointed out the right wing of the aircraft. And if we come up here, look at the bottom, that z-axis is pointed directly out the belly of the aircraft. Okay, so that defines all of the rotations we need to get from the vehicle frame, which again, if we draw that back up, the vehicle frame is aligned with the NED frame. It's just been translated. And the body frame is aligned with the aircraft. Okay, let's jump back over to the notes. So we can now define this rotation that'll take us. So if we do one at a time, we do our vehicle to vehicle 1 frame, and then we're going to do vehicle 1 frame to vehicle 2 frame, and then we'll do vehicle 2 frame to our body frame. That'll give us the aggregate rotation matrix, which goes from the vehicle to the body. Okay, and it's a function, it's a function of our Euler angles. Okay, and recall this was an RZ, RY, and RX, and I can't emphasize enough that this is the version of Euler angles that we're using. You could use up to I think there was 12 total possibilities for Euler angles. So just because somebody gives you an Euler angle doesn't mean it's the Euler angles that we're using. So again, we can see that this is RZ, we can see that this is RY, and we can see that this is RX. Those are our elementary direction cosine matrices. And we multiply them together, we get just this function of phi, theta, and psi. So now we can take a point. This is just a point in the vehicle frame. And we can rotate it and get that same point in the body frame. Okay. Then we're going to design we'll define our aggregate attitude. Sorry, I should have mentioned that because that's the input. Whoops. Missed. There we go. And that's just we'll refer to this as just the attitude of the aircraft. Attitude angles. So we have our three different angles, and we could find that rotation matrix between them. Okay, in the next lecture, then we'll jump in and we'll start looking at our wind triangle.